Hey, Math 180. We are continuing with Chapter 10, Section 2. We're moving on to the ellipse and the hyperbola. So this first video will mostly be about the ellipse. And yeah, hopefully I do some justice explaining this in a good way for you. So in an ellipse, just like with a circle, it has a center here in the middle. And so just kind of layman's terms, we would call this a flattened circle. And so what's going to happen is we have what are called focal points. That's what the F stands for. There's I guess the plural of focus is foci, because there's two of them. I guess I'll write out that each one is called a focus point. But anyway, so what we're going to do is we're going to evaluate, we're going to figure out where these foci are located, and how we create an ellipse is based off of this blue, this black, and this yellow line. And I think you can imagine for a second that the lengths of these lines when I add them together, so the black line all together, is equal to the length of the yellow line all put together, which is equal to the blue line all put together. One book I used to teach out of, I thought did an excellent job of, they imagined for a second that you put a pin, like a push pin, into these two foci, the two focus points, might be an easier way of explaining it. So there's a string, and what you could do is you could take a pencil and you could pull the string as far as you could, and as you tried to pull that string along, it would only reach a maximum distance away. So if you can imagine my pencil pulling that string, the furthest it could get, because of the push pins that are I guess locking the string at the foci, get pulled around. For anybody that's interested in astronomy, you've probably heard of elliptical orbits. That's exactly what's going on. Okay, so there's times that we're a little bit closer to, the center, and then there's other times that we're very far apart. And we have these elliptical orbits going on. So what I'm getting at is that the addition of these lengths are equal throughout, and when I get to a hyperbola, you can use a similar analogy, except it's not adding the two values for a hyperbola. You subtract those lengths, and the subtraction stays constant throughout. So, like if you were to find the distance along this line and the distance along this line, when you subtract those two values, it would be equal to the distance from here to here minus the distance from here to here. And these are still called foci, focal points. But notice the difference is in an ellipse, the foci are inside of the ellipse, whereas the hyperbola, the foci are on, well, I guess you could still say they're inside. They're inside the curves, but they're, on the outside of these values. By the way, we do also call these points on the outside the vertices. So I guess what I'm saying is the foci are inside of the two vertices, whereas in a hyperbola, the foci are on the outside of the two vertices. And you still have a center here in the middle for a hyperbola. So hopefully I've done some justice explaining the difference between the two of them. So as we get into some of the rules, and I'm going to try and keep everything as simple as possible, because this is probably the first time you've ever learned this, is just like with a circle has a center, an ellipse has a center as well. And we label it the same way that we label the circle center, H, K. If I scroll down a little bit, you might actually notice that it looks very similar to the equation of a circle, x minus h squared plus y minus k squared equals, now instead of a radius here, we just have equals 1. And I'll talk about a and b here in a second. So the way that this book explains it might be different than our book, but this makes perfect sense if you follow the way I do this. Is the a value, the way the book, this is set up, is always along the horizontal, because a is underneath x. So x is the horizontal axis, the a value is along the horizontal. So you can see that here as well. Whereas the b value is underneath y, so that's the vertical distance. So whatever this b value is the distance from the center to the top. Now notice that it's b squared, so that's going to make a huge difference as we look at this. And we always, in an ellipse, set it equal to 1. Now notice a few other pieces here is the longer value. If a is longer than b, then a is the major axis. Now I also need to point out that the name major axis goes from one vertex all the way to the other vertex. And we don't, I've seen some books call these covertices, but that I haven't seen every math book call them covertices, so I'm going to hesitate to call them those. So if you see on this picture, the b value is larger than the a value. So then the vertices are from top to bottom. And the major axis is the distance from those vertices, from the two vertices. And then the minor axis would be all the way across there. I'm trying to think if I've missed anything else. I guess they did put a caveat in here that a and b must be positive values, because if we get a negative in there, it might seem like a weird statement. And then we have it has to be a plus in here. If it's a minus, it turns into a hyperbola, which we'll see at some point soon. Okay, so when we're getting ready to graph this, like right now, we're just centered around the origin. If you're confused by what I mean by that, is I have x minus 0 squared, and then this piece would be y minus 0 squared. I don't really like where I put that plus, so let me move that real quick. I'm just going to move that plus down a little bit so it looks like the other problem. And we want the equation to equal 1. You can see exercise 2 does not have it equal to 1. I'll tell you what to do when we get to that. So the only other thing I'm going to do is I'm going to replace 25 with 5 squared. I hope you agree that 5 squared is equal to 25. And the same thing with 4. It's equal to 2 squared. 2 squared equals 4. So what I can deduce from this, I'm going to give you a graph real quick, x-axis and y-axis, is we are shifting the center right 0, up 0. And that's exactly what I was trying to say, is the center is at the origin. The center is at 0, 0, based off of our graph. The fact that the 5 that's squared is underneath the x, then the length of my a value is 5. And so from the center, I can count to the right 5 units. I can also count to the left 5 units. And by the way, when you get to a more difficult math class in college, they might ask you for the length of the major axis. So I don't know if I will ask you this question or if this book will. But for the record, the length of the major axis is double that number. So it's actually 10. Now, if you're going to say, how did I know that was the major axis instead of the minor axis? Is that number was larger than this number, where the b value is 2. So that would be the length of the minor axis is 4. Why? Because you have to go up 2, because it's underneath the y, from the center, and you also need to go down 2 from the center. And I think that's all you really need to come up with a good graph of the ellipse. Right now, I'm not going to concern myself with can you find where the focal points are, or the foci is another math term. So I'm going to stop right there. And you already know I'm going to show you Desmos. So you can make a fraction. We have x squared over 25 plus make another fraction. I'm just hitting the divided by key. Y squared over 4 equals 1. And yeah, you can see everything. The only thing that the Desmos doesn't show you is where the center is located. But I've already talked about that. So I hope you're okay with everything I've explained so far. So I think I have enough time to at least get through exercise 2. And the only thing that's tricky about this one is that this number is not 1. Well, you can quickly fix that by dividing everything by 36. So if I then reduce this problem, well, 9 over 36, 9 goes into 36 4 times. 4 goes into 36 9 times. And that's usually a trick, that they pick numbers that are, first of all, perfect squares, and then 9 times 4 would give me 36. There's kind of a reason why they come up with problems like that, equals 1. So to help you out, and I'm trying to use the same colors, it's x minus 0 squared and y minus 0 squared equal to 1. And let's see, I use this color for the a value. So 4 is the same thing as 2 squared. And 9 is the same thing as 3 squared. So when I go to my graph of this, still centered at the origin, underneath the x value is 2, so I need to move to the right 2, and to the left 2 from the center. And then underneath the y is 3, so from the center, I should have labeled the center, I need to go up 3, and down 3. And so as I connect these points, now it's a vertical ellipse. Up here, I guess I didn't write it down. This was a horizontal major axis, and this has a vertical major axis. So what does that mean is, if I were to go through this, and all you have to say is it's because 3 is bigger than 2, that the major axis now has a length of 6. I hope that makes sense. Please write down any questions that you may have if this is not. The minor axis in this problem is 4. There's 2 on this side and 2 on that side. I guess I didn't say that on the other one. 3 up here and 3 down here. So just to emphasize that I have the correct answer, because you know me, I'm capable of making mistakes, going to Desmos and just typing in the original problem. Let's see, it was 4y squared equals 36. And that hits every point I said it would. And if this is too busy for you, feel free to close out of that. You can see that answer. All right. So I'm going to stop it right here. And we have a little bit of a trickier problem as we move on to exercise 3. Notice that the ellipse still have a plus in here before I get to a hyperbola, which the only thing that really changes is the minus. And there's one other big deal that changes as well. And I'll get to that when I explain hyperbolas before you get to the homework. So I'll see you in at least one more video to explain exercise 3. I could probably get 3, 4, and 5 into one more video, but we'll see.